I remember when my wife and I first moved to the Midwest. I was amazed, first of all, by the scale of farming. You drive through miles and miles of farm fields to get to outcrops. I was also amazed at the soil. Yes, the black color and the clay consistency were unlike anything I had ever seen. But more, the entire economy of the region where I live is literally riding on that soil. To this day, I am in awe of how important that soil is. Yet soil is one of those things that is fundamentally underappreciated. Arguably, there is no more important geologic resource on this planet. Soil is one of these things that you don't know how important it is until it's gone or damaged irreparably. To a geologist, soils are one of the fundamental keys to understanding the landscape. Soils change through time, and they reflect the recent geologic conditions under which they form. Now, it's worth realizing that the word soil means different things in different scientific settings. Engineers use the word soil in a very wide sense to describe anything that isn't bedrock. For example, what a geologist calls sand or even gravel would be included in what an engineer would call soil. That's because engineers are only interested in mechanical properties, so it becomes possible to lump together in a single category all loose material that isn't rock. But geologists study the origins and size of material. For example, sand and gravel are particles of specific sizes that originate from erosion and deposition. So we view soils much differently than engineers. Soil scientists and agricultural scientists think of soils much more narrowly, as a medium for plant growth, so they focus on soil fertility or growing conditions. And of course, the backyard gardener thinks of soil fertility only in terms of the topsoil. That is the stuff that your plants and vegetables grow in. But to a geologist, a soil is both the breakdown product of pre-existing rock and the addition of biological matter. You've got to have both. A geologist would define a soil as a four-way combination: 45% broken rock material, 5% organic matter, also known as humus. What's the other half? Soil is typically 25% water with dissolved materials and 25% air. Yes, there's a lot of air. This is also why geologists describe soil as the intersection of Earth's atmosphere, hydrosphere, biosphere, and lithosphere. Soil is literally where they all come together. A soil forms essentially parallel to the air-Earth surface and is made up of layers called horizons. Those soil horizons result from the alteration of the underlying bedrock or unconsolidated geologic units. It's an alteration that occurs through physical processes, chemical processes, and biologic processes. Physical processes include material fracturing as a result of things like freezing of pore water. Chemical processes include weathering of feldspar and other minerals into clay. Biological processes include plant material breaking down and changing the composition and texture of the underlying material as it is washed downward. Soils are important beyond their ability to provide a medium and nutrients for healthy plant growth. Soils are also important because they influence the quality of the water that moves through them. Both rainwater and irrigation water go through important filtering processes as they move through the soil horizons. Soil is also important for the planetary storage of carbon. Organic matter breaks down in soil, and the carbon component of that breakdown process is stored and later used by plants. But if soils are disturbed, carbon is released in the form of atmospheric CO2. We now understand it is important to try to leave that carbon where it is. The disruption of soils is an important consideration when thinking about atmospheric carbon systems. Soils form through the process called pedogenesis. The root pedo refers to soil and shows up in a lot of the terms associated with soils. Pedology is the study of soils. Pedosphere is the soil-based layer of Earth's crust, and so on. So soil making, or pedogenesis, involves the weathering of geologic materials, the disintegration or decomposition of rock in place. Weathering results in an unconsolidated or loose mineral composition and the generation of clays and chemicals. Weathering doesn't always result in soil, though. If the weathering process results in the dissolving of materials, such as with limestone, obviously there's no mineral material to make a soil out of. Additionally, pedogenesis has to involve the addition of organics. If there's no organics contributed to the rock that's broken down, there is no soil. Geologists call weathered rock saprolite. The rock is weathered, but no organics have been added, so not a soil. Organic processes occurring on and in a soil contribute decaying organic matter and result in further breakup of mineral material, and importantly, add nutrients and microorganisms to the mix. Finally, a downward movement of particles and ions called translocation, which usually takes place in solution, results in the formation of the soil layers called horizons. Horizons make up the soil profile. So when you think about it, the soil that forms in a given location is really a function of the underlying geology, what geologists call parent material. For example, soils on granite tend to be acid and clayey depending on the crystal sizes of the minerals in the rock. Limestone bedrock sometimes dissolves completely, so they have thinner soils. However, a limestone-rich gravel or glacial till can be very good agricultural soils, rich in nutrients. But the old idea that soils are entirely a function of their parent material has given way to an awareness that soils are also a function of 4 environmental factors. The climate of an area, temperature, the amount of rainfall, prevailing weather patterns. Dry areas have very little organic contribution. Cold areas have limited amounts of weathering, and wet areas have a great deal of both weathering and translocations of soil clays and chemicals. The topography, how steep or flat the land is, can influence the movement of particles. Hill slopes tend to have thinner soils because gravity results in the movement of soil particles downslope. Valley bottoms, on the other hand, tend to accumulate those soil particles that have moved downhill and tend to be thicker. Vegetation, contributed organic materials, organic activity, and organic acids can alter both the color and thickness of a soil. Prairie soils are black, a result of the buildup of carbon that resulted from millennia of grass fires. Forest soils tend to have a thick organic buildup. And finally, time. How long a soil is forming is reflected in how distinct the horizons are and how thick the soil is. So let's look at a soil and find out what makes soil so great. For a geologist, the way to describe a soil is with a soil profile, which is defined on the basis of the horizons that are in it. Most people that work with soils think in terms of at least 4 master horizons. That is, there are certain horizons that show up very consistently. They are easy to recognize, and they provide really fundamental information about a particular soil. The surface and uppermost part of the soil profile in many places is a dark gray or black layer that contains organic material, and this is called the O horizon. This is the result of organics collecting and decaying on top of the original parent material, whether from roots, leaves, or decayed woody material. Nearest the surface, the organic material of the O horizon is frequently recognizable. You can see leaves or pine needles, seeds or nuts, and you may recognize the type of plant that the material came from. Conversely, there's an absence of mineral particles. A little bit deeper though, and the organics have decayed to a point where you cannot identify the original plant. The organics have decayed to amorphous black organic material. Below the organics of the O horizon, the names for the next three horizons go in alphabetical order, starting with the A horizon. The A horizon is that part of the soil that receives organic material from the O horizon and loses material to the horizons below. In places where there is a lot of organic material being produced, like the prairie soils of the upper Midwest, the A horizon is black. So depending on where you are, the color of an A horizon can be either very light or very dark. The leaching of material from one layer to another is called alluviation. So the A horizon is sometimes known as the zone of alluviation or the leached zone. There are some A horizons that are so leached, like those that underlie pine forests, that they can look white or gray depending on the amount of organic material in them. Below the A horizon is the B horizon. The B horizon is known as the zone of accumulation or the zone of alluviation, the opposite of eluviation. Very fine-grained material, such as clay minerals, is translocated downward into the B horizon, which as a result usually has the most clay in the soil profile. It's the clay that gives the B horizon such distinctive characteristics. Clays, as they are translocated, will coat the small drainage passages through which they're transported. What happens is that the clays will then accumulate in those passages, coating the walls. This is the process that results in the formation of what is known as soil structure. When you excavate a soil, as you begin to get your eye in, you will begin to see patterns. Some of those soil patterns will look like columns, while others will look like prisms. Even smaller, in undisturbed soil, you are likely to see small blocks of translocated clay known as PEDs. The last of the four common master horizons is the C horizon. The C horizon is essentially weathered parent material. As you get below the B horizon, you'll see a change of color and a depletion of clays. By the time you reach the C horizon, you've reached the lower limit of pedogenic processes. In many cases, patterns that reflect the original sedimentary or metamorphic patterns of the parent rock are now visible in this layer of soil. Essentially, you are at the base of the soil. Of course, there are variations in the master horizons, depending on conditions. Some soils can have 5 horizons. Sometimes, just below the A horizon is a portion of the soil so alluviated that it deserves recognition as a distinct layer. This is referred to as the E horizon. E horizon is short for eluvial horizon. In the E horizon, everything has been removed except for the residual crystalline material, such as quartz or other minerals that are resistant to weathering. Below the C horizon, soils can sometimes have an exceptional buildup of calcium carbonate at depth. This is called a K horizon, also known in some places as a hard pan. So let's talk about tools to use when looking at a soil profile. A soil scientist or a geologist would have a soil auger like this. This is essentially a corkscrew for soil sampling. If you don't have one, what do you need? Really, not all that much. If you're simply trying to understand what type of soil you have in the backyard, you can use a small shovel or a trenching shovel or a flat-bladed landscaping shovel. But even a small gardener's trowel usually does the trick. A tape measure is handy if you're interested in comparing soils in one place or another. After that, it's really just about dirty hands and careful observation. I promise this won't hurt the landscaping. But if you're nervous about it, see if you can find an excavation or a road cut where you can safely look at a soil. So first, as you start to dig, notice the O horizon. In a lot of places, the O horizon can be really tenacious. It's the organic mat and roots that are holding tightly to the soil. When we talk about soil erosion, I'll bring this property up. Make sure you're digging a straight side to your hole It will make observations easier. As you dig deeper, notice what happens. You start to hit mineral matter, and digging probably gets easier. For now, don't dig any deeper than a foot or so. Let's see what we have. The O horizon won't have crystalline material, and if you slice through it with a knife, you shouldn't hear or feel a scratching sensation. Once you do feel the scratches of a mineral material, you're probably in a different horizon. Take some time to look at the components of the O horizon. You can see what plants the organic material came from. Is there much organic material there at all? If you can readily identify all the plant material, or if there isn't very much organic material at all, it's a very thin O horizon. Then you might be dealing with a very young soil or a sod layer that a contractor placed over landscape fill. This isn't bad. It doesn't mean you couldn't have a garden. It just means that the original soil has been stripped away, probably during the construction of the neighborhood. But for a soil profile formed over a longer period of time, there will be an O horizon that has recognizable plant litter at the surface and black organic particles below. Now focus on the A horizon. What does it look like? Is it light colored? Is it dark? In the western part of the U.S., a lot of soils have characteristically thin and light colored A horizons. In the east, a lot of soils are so leached because of the high amount of rain that they have those highly eluviated E horizons, which might even appear white. In the prairies of the Midwest, grass fires and the regrowth of the prairie grasses, followed by more grass fires, have resulted in soils that are loaded with organic material, leached into the A horizons, and these will be black. The B horizon is where clays are deposited. If you have a buildup of clays in the B horizon, you should be able to see it in the soil structure. Even better, you should be able to feel it with a knife. Start at the top. Stick your knife or trowel into the soil profile. Slowly move your knife downward, like you're cutting a cake. As you transition from the O horizon to the A horizon, you feel or maybe even hear the scratching of mineral material on the blade of your knife. Now as you continue pushing your knife downward, it won't be as scratchy. The clays in the B horizon won't apply friction to the blade. So in a clay B horizon, your knife will move through it quietly. I must admit, this is something you have to practice, and you have to consistently use the same tool. Okay, so what to use? I started out just using a folding pocket knife, but that's how you cut yourself. You really need a good lock blade knife, like this one. I've been on field trips with folks who focus on soil full time, and one of the things I've learned from them is that if you're going to use a tool for soil analysis, always use the same tool. There are many of them who will show up with these Crocodile Dundee Jim Bowie knives that have no other use whatsoever in the real world. I was in a wedding party of a fellow geologist, and the gift he gave to the groomsmen was a good lock blade soils knife. That was a great gift, and I held on to that one for a long time. So what do you think? Soils are cool, right? And it's not as hard as it might sound. If you have ever dug a hole in a soil, then you already know that they are not uniform. All you have to do is think about what exactly changes as you dig deeper. Is it harder to dig or easier the deeper you get? That might be due to changes in clay content. Is the material you are getting out of the hole changing color? It could be due to organic matter or getting down to unweathered parent material. Feel the stuff as you dig it out of the hole. Clay? Sandy? These observations are what soil science is all about, and you can make these observations with very little practice. You can even get a little help. The United States Department of Agriculture Natural Resources Conservation Service Soil section has a website. On it, you can access soil surveys of your area. Soil surveys are county-level studies done by soil scientists and made available to the general public. They include both soil maps and soil descriptions. Use the online map to find out the name of the soil you are studying, and then look up the description that is included in the survey. I bet that even your first soil description will be pretty close to the professional one. That website has a wealth of information on soil types, soil uses, and even soil conservation. They even have a soil color poster of every state. Does it get any better than that? Now let's talk about the soil horizons that result in a fertile soil. For example, soils in a forest can be very fertile, but it depends on how much weathering is going on in the A and B horizons, and how much material is translocated out of the A horizon. What determines the amount of minerals in a soil are the parent material and the amount of weathering that has taken place. If the soil is under very wet and warm conditions, especially with acidic plants, that soil will be relatively infertile. Soils that form in grasslands frequently have abundant organic matter and can be very, very fertile. The cycle of prairie fires and regeneration of prairie grasses that has happened for thousands of years in the Midwest has created some amazingly fertile soils. The frequency of grass fires and the speed with which grasses can regenerate results in an almost constant addition of organics to the soil. Although forests accumulate a lot of organics, they can't produce them at the rate that grasslands can. And they also produce a lot of acids, and soil nutrients are frequently leached away. In deserts, although there isn't much organic matter, if there's enough mineral matter, you can still have a fertile soil. A final example is wetland soils. Wetland soils can be really nutrient rich, but if there's too much moisture, say a wetland where the water table is near the land surface, only bog plants will grow. Soil fertility really does vary. What are the specific characteristics that increase soil fertility? An important one is nutrients. Gardeners and lawn folk are all over this. Nitrogen, phosphorus, and potassium, as well as lesser amounts of calcium, magnesium, sulfur, iron, and other elements really help a plant grow. Before adding nutrients to a soil, make sure you have it analyzed. The right geology may eliminate the need for nutrient additions. If the parent material already has a certain group of elements, adding more of those same elements can create problems. Soil acidity between 6 and 7 pH is usually fairly optimal, but again, conditions change. I once planted a variegated maple in my yard. They like an acid soil, so less than a pH of 7. The poor thing struggled for years. I talked to a university tree specialist about it. She was cutting one down on campus, hence the conversation. She said there were two choices. For the foreseeable future, treat the soil to make it more acid, or plant a tree that was better suited to the limestone-rich soil that I have, where pH is greater than 7.5. Of course, as with soil acidity, you can modify the soil nutrient content by adding commercial fertilizers, compost, and manure. But you have to be careful, both on behalf of the plants you want to grow and the environment in general. Inappropriate uses of nutrients can lead to both reducing the fertility of the soil and polluting the surface and the groundwater. If you're having trouble getting something to grow, you should seek specific help. Maybe even bring a sample of the soil in for analysis. Before applying fertilizers, learn as much as you can about both the soil you'll be working with and the nutrient needs of your chosen crop. And of course, you should always follow directions carefully when working with any chemical. One of the ways soil and geology can influence plants is specifically in the fruit of plants. In wine production, there is a concept called terroir. This is the idea that grapevines, grapes, and ultimately the flavor and quality of the wine made from those grapes is influenced by the local habitat, the terrain, the climate, and soil geology. Let's talk about one more thing in terms of soils, and that is soil erosion. Geologically, most scientists would agree that human beings are exceedingly significant contributors to the shaping of the landscape. Indeed, humans are the ultimate geomorphic agent. Geologists estimate that human activities shift 10 times the amount of material on the Earth's surface as all superficial geologic processes combined. One study suggested that humans move 45 billion tons of geologic material every year. One of the negative results of all the landscape modification that humans do is the loss of soil. Each year in the United States, what has been estimated as perhaps 4 billion metric tons of soil erodes from the land surface. Most of that erosion is due to human activity, agriculture, excavations, and poorly designed drainage systems. On a human timescale, that soil is not renewable. About half of this lost soil is from existing cropland. And it's not just in the US. The United Nations estimates that from 1950 to 2000, more than 1/3 of the world's farmable land was lost to soil erosion. How does this happen? When you break up the soil, either by excavation or by intensive farming, two things happen. One is the reduction of organic matter in the form of roots that hold together the soil. The other is the breaking up of soil structures, those clay-coated components of the undisturbed soil that help it keep together. If you've ever tried to start a garden in the backyard or even dig a small soil trench, you know how difficult it is to break up that O horizon and the B horizon layers of clay below it. Certainly, the result of intensive tillage is a soil medium that can readily be planted. That is why a soil is tilled, to grind away unwanted plants and clear the soil for new plants. But what once was a soil profile is now broken up into small particles that are much more subject to erosion. The extent to which the soil is disturbed depends on the implement, the amount of material moved, and the depth of the soil agitation. Intensive tillage is defined as the destruction of 85% of surface plant material crop residue. That's previous crop remains and weeds. This is accomplished using implements consisting of discs or chisels pulled by a tractor. In addition to reducing the cohesiveness of soils and thereby increasing erodibility, intensive tilling can also negatively impact soil fertility. In the United States, about 2/3 of soil erosion is propelled by running water, and 1/3 is propelled by wind. The problem is that erosion by running water is exacerbated by the creation of open fields that are left bare after harvest. Rainwater doesn't infiltrate as quickly on bare fields as it does on a field that has vegetation cover. That results in more runoff, faster water velocities, and more erosion. Similarly, wind can erode a bare field much more quickly than a field covered by vegetation. Fine-grained particles are disaggregated and loosely packed in a tilled soil. Additionally, there is no vegetation to curtail the wind velocities. The result is an increase in the amount of wind erosion. The saddest example of this was the Dust Bowl of the 1930s. Low rainfall amounts and overplowing, that is, tilling the soil too fine, resulted in incredible amounts of wind erosion. There were times when dust would cover a landscape up to 100 meters in height. A single storm in April of 1935, referred to as Black Sunday, eroded 300 million metric tons of soil from the Great Plains and deposited that material along the Atlantic coast, where it fell like fine snow for 2 days. Things have certainly come a long way since Dust Bowl times, but still there is a need for practices that will keep the soil where it is. This includes what is called no-till farming, which means drilling small holes to plant the seeds without making a furrow. To lessen the amount of water erosion, steeper agricultural slopes should be terraced. Terraces create flat spots, which will slow down surface water flow. You can slow down runoff by planting rows of crops parallel to the elevation contours. Finally, keeping cover crops throughout the year allows for more infiltration of water while also reducing wind-based erosion. No-till farming also makes sense economically. It not only lessens erosion, but farmers can decrease immediate costs as well. By eliminating tillage, you reduce fuel costs, you lower the wear and tear on equipment, and shrink fertilizer costs. No-till farming also results in more infiltration and preservation of groundwater supplies. There are lots of advantages. In terms of economic value, there is no geologic resource greater than soil. And yet, it's something easy to take for granted. When you get the chance, take a look at a soil, see the horizons, and see the changes that are taking place through the complex interaction of the physical, chemical, and biologic processes that make a soil. And I can't help urging you to go ahead and get dirty. Enjoy yourself and enjoy soils.